This is lesson number 8 of the Quantum Mechanics, a mini lecture series titled the Photoelectric Effect. So around the same time as Planck introduced his black body radiation formula in 1899, Philip Lenard used beams of light and he fired them at thin metal foils. So a physicist named Philip Lenard took slabs of metal and he fired light at the metal, and he found an interesting result. He actually found electrons from the metal being ejected. Okay, so light ejects electrons. That was Lenard's observations. Okay, this is called the photoelectric effect. Photo is Greek for light. Electric, think of electricity. So light is causing electricity. Okay, even though Heinrich Hertz noticed this 10 years ago, 10 years before, I should say, Lenard made, 10 years before Lenard actually made more precise measurements. And here's the experimental setup that Lenard used. Goes something like this. You've got an emitter, collector. You've got light coming in. So the emitter in this case, that's the slab of metal. Collector, and you've got what's called an ammeter. An ammeter is just a device which measures current. And you've got like a plate here, plate that's connected to a battery. I'm just going to draw it like this. It's not really scientific, but anyway, connected to the metal emitter. Okay, so the idea was that light would come in, strike the metal, the emitter, that would emit electrons, and the electrons would make their way towards the collector. Now, here's the interesting bit. When a voltage was added between the emitter and the collector, the voltage, I should say, between the emitter and the collector can be varied, and this actually affects the measured current. Okay, there's a voltage here called the retarding voltage. Okay, and voltage is just basically another way of saying push, loosely speaking. It's a push or a force that pushes electric charges like electrons. Okay, and the flow of electrons, that's called a current. Okay, so the retarding voltage is a voltage that opposes or slows down the motion of electrons in this case. And what was found was that the current, I should say the photocurrent, okay, the electrons emitted as a result of the light coming in, decreases sharply when the retarding voltage was increased. Retarding voltage increased. Okay, why is that? Because the collector here became more negatively charged, because electrons were making their way towards the collector. And the emitter became overall positively charged, okay? So metals, any other object in the universe, they're neutral. They've got no electric charge. As soon as you add electrons or take away electrons, they become charged, okay? So the emitter is losing electrons, so therefore it's got a net overall positive charge. There's, at a very specific value of retarding voltage, let's call it V sub 0, at a very specific value, no more photocurrent appears, okay? So let me draw a graph of this. Okay, let's call this retarding voltage. Let me give it some value here, V sub O. Let's call the y-axis photoelectric current. In other words, the electrons being ejected from the metal. Below V sub 0, you get no current at all. Okay, 0. X-axis is 0 here. But above that, you get current. You get current flow like this. And that's the photoelectric effect. Okay, there needs to be light striking a metal surface in order to get electrons flowing, to get a current out of that. Okay, and it's from intuition, it makes sense. If the force is great enough to prevent electrons from being emitted from the metal, you won't get any photoelectric current, as demonstrated by this graph. So far so good. But in the next video, you shall see that there's going to be some weird things popping up.